Now we are ready for the washer method. And so this is very similar to the disc method, only the circular shape on the edge will have a hole in it. So if you've ever, I'm sure you've probably seen a washer before. Here are a couple I got out of our garage. It's a circular shape with a hole in it. And so that's the shape. So if we need to calculate the area of a washer, it is just the subtraction of two circles. So where this is a hole, right? So if this is the center, we have two radiuses here. We have an outer radius, which I like to call capital R. This is just how it makes sense to me. And then we have this inner radius, which I call little r. So if we needed to calculate the area of the washer, it's going to be the area of the entire big circle, pi r squared, minus the area of the hole, the inner circle, minus pi r little r squared. R outer minus R inner. You can factor out the pi. So the area of the washer is pi times the radius, the outer radius squared minus the inner radius squared. All right, so in the book it'll say R outer, R inner, and I just used big R and little r for myself. Okay, so that is what our area is going to be in these examples. So we've got just 3 examples here. Example 6 says find the volume of the solid that results from rotating the region enclosed by the curves y is x and y is x squared about the x-axis. So first let's draw that and see what that looks like. So y is x squared about the x-axis. This is example, what is this one? 6? We're already on 6? Is that right? Okay, well, did I skip one? Yeah, I think that's the wrong number. I'm going to change this to 5. Because I don't think that is right. Anyway, here we go. This is find the volume of the solid that results from rotating the region enclosed by y is x squared about the x-axis. So let's draw it. Y equals to x is the line with the slope of 1 and a y-intercept of 0. 0, up 1, right 1. This is y is x. Looks like this. All right. And then y is x squared. This is a parabola centered at the with the vertex at the origin. So at 1, when x is 1, 1 squared is 1, 1, 1. This is where these guys are going to intersect. So this little region, that's what we're interested in right here. This is what we're going to rotate. And we're going to rotate it about the x-axis. Okay. So when we do that, this is what it looks like. Okay. So if we were to spin this around and around and around, you would have a resulting solid. And if you were to look at the center of this, you're going to have an outer radius. So let me see if I can sort of draw the circles on here. You will have, like, let's just take a slice here. We'd have an outer radius of the line y equals x and an inner radius of the curve x squared. So when you draw your cross section, which is what this is, my outer radius is the one that is from the x-axis all the way up to this part, which is the line y equals x. And the inner radius only goes to this curve, which is x squared. That's what my inner radius is. All right, so let's see. I'm integrating, my slices are going horizontally, so that means it's a dx. I'm going to be integrating from 0 to 1. These guys intersect at the point 1, 1. That's how I figured out how far to go. So from 0 to 1, pi outer radius squared, which I said that was x, minus inner radius squared, dx. And this is what I'm integrating here. So when we integrate this, this is going to be x squared minus x to the 4th dx. From 0 to 1, this is going to be x to the 3rd over 3 minus x to the 5th over 5. From 0 to 1 times pi. Pi, if you substitute in 1, it's going to be 1/3 minus 1/5. And then if you substitute in 0, you're going to get a big 0, so minus 0. If I get a common denominator here of 15, 3 times 5 is 15, 1 times 5 is 5. 5 times 3 is 15, 1 times 3 is 3. This results in 2 over 15 times pi. That is the area of this region rotated about the x-axis. Okay, let's go for example, the next one. I think it's number 6. I think my numbers are off on my sheet. So it says, find the volume of the solid that results from rotating the region enclosed by y is x and y equals x squared. This same region, y is x and y equals x squared, about the line y is 2. So not about an axis, but about a different line. So let's think about how that one's going to go. All right, so this is going to be, let's see, y is x squared about y is 2. Oops, let me make myself some more room. Y is x, y is x, y is x squared about y is 2. All right, let's see what this guy will look like. So here is my xy. Okay. Here is my xy. Okay. Now, y equals to x is still the same line. So here it is. Y equals to x. Y equals to x squared. Looks like this. So this is my region. So this is the point 1, 1. This is the point 0, 0, 0, 0, 1, 1. Okay, so this time it's about y is 2. So maybe I have to make more room because I have to go up taller. So I'll write this stuff over here. Y is x, y is x squared about the line y is 2. Okay, so if this is 1, then I need to extend my y-axis up so I can see what else is happening. So 1. Okay, this is 2. This is what I'm rotating it about. Y is 2. Okay, this is y is 3, and this is y is 4. Okay, 3, 4, and this is y is 5. Okay, so if I'm rotating this about this line, if I rotate it, it's like reflecting, right? This is the blank space, and so this is where my curve starts, right here. And if I rotate this up, it's going to look like, I'm sorry, you have to think here. This is my curve. It's going to look like this. Let me just see if I like that. Yeah, I do like that. Okay, that's what it's going to look like. So, if this is spun around, it's not rotated, it's rotated, we can form a solid. And so this solid will, if I take just a slice somewhere, let me just pick some arbitrary slice right here. Let me slice it here. What is this going to look like? Well, my outer radius is going to be here. I have to picture this, sorry. So my outer radius is going to be like here. And I'll have this inner radius here. Wow, that looks so bad. Okay, let me try this. Okay, so I'm going to have a washer look right here. So let me do... I always draw this little cross section, which makes me feel better. This is my inner radius, R, and then I've got my outer radius, big R. So let me think. If I'm slicing this, I am slicing it horizontally. So this is going to be a dx. Okay. I'm going to be going from 0 to 1. My slices are going to be from x is 0 to x is 1. 0 to 1. Okay, Okay, now I need to think about my radiuses. It's pi times the outer radius minus the inner radius, both of those squared. So my outer radius is going to be from here to the curve, x squared, right? But we have adjusted this. It's not from the x-axis. It's from this line y equals 2. So the distance from here to here is really 2 minus this curve. Or if I go from here, it's really 2 minus the curve, x squared. So that is the outer radius. Big R is 2 minus x squared. Little r, because we didn't go from the x-axis, but we came from y is 2, is going to be 2 minus the line, y is x, 2 minus x. So when we integrate this, it is big R squared, 2 minus x squared, minus little r squared, 2 minus x squared with respect to x. This is what we're integrating. So let's just integrate it. This has a little bit of algebra to it, but it's not that bad. Let me make a little room over here from this other example. Now, if you're not being, like from my drawings, I can appreciate the fact that they're not that great and that you need to be able to see something better. The textbook has some really good looks of how what these solids look like spinning around. So you should be looking at that to get a better picture of what's happening here. Okay, so right here, let's finish this integration. So this is pi from 0 to 1. Let's do this multiplication. If I square this is going to be 4 minus 4x squared plus x to the 4th minus 4 minus 4x plus x squared dx. I'm going to distribute the negative, so it's going to be 4 minus 4x squared plus x to the 4th minus 4 plus 4x minus x squared dx pi 0, 1. All right. 4 minus 4 is 0. 4 minus 4 is 0. Okay. Collect like terms. Who's alike? We've got negative 4x squared and negative x squared minus 5x squared. We've got a plus x to the 4th. We've got a plus 4x. Now we can integrate. This is going to be negative 5x3 over 3 plus x5 over 5 plus 4x squared over 2 from 0 to 1. This is going to be pi times negative 5/3 when I substitute in the 1 plus 1/5 plus 2 minus 0. If I get a common denominator again of 15, 3 times 5 is 15. Negative 5 times 5 is negative 25. 5 times 3 is 15. 1 times 3 is 3. This is 2 over 1. So I would say 1 times 15 is 15. 2 times 15 is 30 times a pi. 30 minus 25 is 5, plus 3 is 8 over 15 pi. This is the area of this curve rotated about the line y is 2. Okay, last example for washers. Find the volume of the solid that results from rotating the region enclosed by y is x and y is x squared, the same region about x is negative 1. All right, so let's do it one more time. Here we go. Same region. Y is x. Y is x squared. X is negative 1. Okay. Here we go. Y is x. Y is x squared. Okay. This is our region. 0, 0, 1, 1. But this time it's about, oops, let me move this guy over here. 0, 0. This time it's about the line y is negative 1. X is negative 1. So go over here to x is negative 1. And this is what we're rotating it about. So this is a vertical one. All right, so if I rotate this, it's going to be like this. I almost didn't leave enough room. If I rotate it about x is negative 1, it's going to look like this. I really didn't leave enough room, but I'll move it over just a little bit. Just a little bit. We'll call this one. So this is x is negative 1. So this means we go right here. That's better. All right, so we're rotating it about x is negative 1. So we rotate it, we spin this around, right? Then we get some resulting solid, which has an inner and an outer radius. So okay, this should be circular, but this is my outer radius. This is my inner radius. Okay, and this time, my thicknesses of my circle, I'm moving up and down. This is a dy. I spun about something, a vertical line, so it's with respect to y. So how low am I going? From 0, from this 0, this y is 0 to this y is 1. Look at the y's. So 0 is 0 to 1 dy, and so it's going to be pi times the outer radius squared minus the inner radius squared. Okay, let's have a look at the outer radius. The outer radius is from here all the way to here. The outer radius is from here all the way to here. That is the big R. All right, let's think about what that is. This is really, if we were here at the origin, this would be the distance to the curve, x squared, plus another 1, because we've added this other 1. So the big R is the curve, x squared, plus a 1. However, we need it in terms of y. So solve for y. So x is the square root of y. So the radius, big R, is going to be the square root of y plus 1, because we added this 1. Or the square root of y minus negative 1. You can think of it that way. The distance is the subtraction of the two. Okay, little r is from, if we were just at the x, it'd be to y is x, or x is y. But we add this additional 1 on here, so little r is going to be this curve, y plus 1. All right, so r squared, capital R squared, is going to be the square root of y plus 1 squared. Little r is y plus 1 squared. So this is going to be pi. Square root of y squared is y plus 2 times the square root of y plus 1 minus y squared minus a 2y minus a 1. Let's see, this is y squared plus 2y plus 1, but the negative gets distributed. dy. So let's see, this is going to be pi from 0 to 1. Let's see, is there anything we can add up? We've got 1y squared, or a negative y squared. Let's see, a negative y squared, got that guy. What about the 1 and the negative 1? Add a 0, okay, that's gone. We've got negative 2y plus a y, which is a negative y. All right, and then what's left? This is taken care of, this is taken care of. I got the y squared up there. What's left? 2 square root of y plus 2 square root of y dy. Okay, let's integrate. Minus y cubed over 3 minus y squared over 2 plus, okay, let me think of this as a y to the 1/2. Plus 2y to the 1/2 plus 1 is y to the 3/2 times 2/3 times 2/3. And this is from 0 to 1. All right, let's evaluate this guy. So it's pi times negative 1/3 minus 1/2 plus 4/3 when I plug in 1, and then a big minus 0. All right, let's see, this is going to be a 6. We'll get my common denominator. 3 times 2 is 6. Negative 1 times 2 is negative 2. Times 3 times 3 times 2 times 2, 8. 8 minus 5 is 3. Is that right? 8 minus 5 is 3. This is 3 over 6 pi, or pi over 2 is what I get right there. The area of this guy rotated about that. So, all right, that's washers.